Very good, very well. So let me warmly welcome all of you to our Friday seminar series, which is a joint effort of several universities from different continents. And let me briefly introduce Friday seminar series, but let me start from slide number 1, not from the very last one. So my name is Vladimir Terzi. I am full professor at the Skolkovo Institute of Science and Technology in Moscow in Russian Federation. And this year, we jointly with Shandong University, with National University of Singapore, with Delft University of Technology, Indian Institute of Technology Kanpur, and Warwick University, we started this Friday seminar series. And by now we have accomplished the spring series. And now today we're gonna start with our fall series, what we're starting from October. And all right, next to me, we have a technical chair, Professor Lei Ding from Shandong University, and our fantastic team, our secretaries, Dr. Wei Yu Bao and Ms. Tian Hang. So without two of them, everything would be much more difficult, but thanks to them, the entire organization is going very smoothly. As I have mentioned, we have different professors and those who are contributing to the organizing committee, including Professor Saikat Chakrabarti, IIT Kanpur, Mazhar Karimi from University of Vasa, Finland, Mustafa Keshti, postdoc from Warwick University, Dr. Alexandra Lekic from Technical University of Delft, Dr. Marian Popov from Technical University of Delft, Professor Jovan Mikulovic from Faculty of Electrical Engineering from Belgrade, and last but not least, Professor Nilanjan Senroy from IIT Delhi. From Skoltech side, the organizing committee are David Pozo Kamara, Elena Grazina, Federico Martin Ibanez, and Piotr Vorobiev. And these are participants, which I have already mentioned, and the list of our fall part is given in this part of this slide. We will have Tian, Radarashi, Alexander, Stepan, Mostafa, and Dong, who are gonna be presenting us every week their presentations, their contributions. Today, I'm very happy to introduce Mr. Tian Hang from Shandong University from China. He will tell us something about non-iterative multiple energy flow calculation using data-driven modeling techniques. So, well, let me now stop sharing my screen. Let me now introduce Hong Tian. The stage is yours, so please start your presentation. Thank you very much, and thank you very much to all of you attending this event.
Thank you very much, Professor. Can you hear me? Can you hear my voice? Is that okay?
Yes, oh, very well, great. Excellent.
Okay, and now I'm going to share my presentation. Okay. Oh, sorry.
If you need some help, just let us know.
Okay, no problem.
Excellent. We see your presentation. Excellent. Thank you.
Thank you, Professor. Hello, everyone. I'd like, first of all, to thank the organizers of this meeting for inviting me here today. Let me introduce myself. My name is Tian Hang. I'm a PhD student in School of Electrical Engineering at Shandong University in Jinan, China. And I'm currently working in Professor Haoran Zhao's team. And as you can see on the screen, our topic here today is non-iterative multiple energy flow calculation using data-driven modeling techniques. So in this talk, we would like to concentrate on the energy flow of a larger system, the integrated energy system, which contains typical energy flows like electricity, heat, and natural gas. And we are going to model this energy flow in a data-driven method. I'll divide my presentation into three main parts. I'll begin with an introduction of the general background of integrated energy system and multiple energy flows. Then I will move on to introduce our formal work about a dual-driven modeling approach for electricity heat flow calculation. After that, since the presentation time is limited, I'm going to have a very brief abstract of our recent work on a dual-level surrogate structure for interval probabilistic multiple energy flow calculation. The figure on the following slide shows the percentage of renewable energy in total thermal energy consumption, which are divided in three sections: heating and cooling, transport, and power. As you can see in the figure, despite the fact that heating and cooling account for 51% of worldwide terminal energy consumption, only 11.2% is produced from renewable sources, compared to 28% in the power industry. So there is still much room for improving. Therefore, the low carbon energy transition is still struggling with the problem of achieving synchronized and sustainable development across multiple energy systems. This figure shows multiple energy flows in an integrated energy system, namely IEF. The energy flows firstly come from fossil fuels like coal or gas, and renewables like hydro, wind, and solar power. Energy flows are then going through networks like pipeline, power grid, or heat and cold distribution. They are also going through the energy conversion equipment and may transform into another type of energy. Finally, energy flows are going to the terminal demand of heat, cold, gas, and electricity. The IEF aims to break down the barriers between traditional isolated energy systems and boost the overall efficiency. And it will firstly improve the operating flexibility and expand the control boundaries of power systems. Secondly, it will promote the use of renewable energy in heating and cooling systems. At last, it will increase the efficiency of the whole energy system and support the low carbon energy transition. This figure shows a more detailed illustration of how multiple energy flows, namely MEF, connecting devices and different networks. To properly operate and control such a complicated IEF, the acquisition or forecasting of network states like bus voltage, water temperature, or gas pressure provides critical information for both decision makers and the automated controllers integrated in the system. This can be realized by the calculation of MEF. In the second part of this presentation, we will focus on data-driven MEF modeling. And in the third part, MEF calculation considering uncertainties will be introduced briefly. In the following slides, I'm going to introduce some current challenges in MEF calculation. With the lack of fossil fuels and high penetration of renewables in MEF, the nodal energy injection is subject to large amplitude, wide area, and high frequency fluctuation. Therefore, the MEF state is evolving faster and more complicated. However, the traditional MEF calculation based on physical model is time-consuming, since it's based on iterative solution of implicit nonlinear equations. Therefore, the MEF calculation method with high accuracy and high speed are urgently needed to realize the rapid perception of and online regulation of MEF state. As we can see in the equations on the left-hand side, the essence of MEF calculation is to solve nonlinear energy balance equations, which is similar to the form of power flow calculation. MEF calculation is an essential component to support planning, operation, control, and safety evaluation of an MEF. Newton-Raphson method, which is illustrated in the figure on the right side, is the most commonly used calculation method in power system and MEF at present. The core idea of this method is to transform the solution of nonlinear energy flow equations into the solutions of linear correction equations by successive linearization. Its advantage is that the number of iterations is basically dependent of the scale of the network. However, the modified equation needs to be reformed and calculated in the process of each iteration, resulting in long computing time. In addition, the convergence reliability of the algorithm depends on a good initial value. If the initial value is not chosen properly, the algorithm may not converge or converge to a solution point that cannot be run. To sum up, the first challenge is to find a non-iterative method to calculate MEF efficiently. In recent years, with the wide development of measurement devices in electrical heating systems or other types of energy networks, the acquisition of history and real-time measurement data is getting much easier. The development of data-driven MEF calculation and analysis provides an effective way to overcome the problems of inaccurate parameters, time-consuming iterative calculation, and unguaranteed convergence. Before introducing our proposed method, I'm going to talk about the data availability issue. Due to the consideration of independence, security, and privacy of the system from the operators, it is not easy to obtain a large number of snapshots from the two networks simultaneously. Therefore, the measurement data is currently not considered in this work. As an alternative, like most related literature do, we choose to use simulation data, which is generated from iterative calculation. The difference between simulation-based data-driven and measurement-based data-driven is that the former one can still approximate and accelerate the calculation of original model, but it is incapable of dealing with the problem of inaccurate parameters. In this section, an integration of mechanism-driven and data-driven, namely the dual-driven approach, is proposed to generate more accurate linear models for MEF calculation. The framework of the integration process contains the following four modules as illustrated at the top of this page. There are four modules: data preprocessing module, mechanism-driven module, embedded data-driven module, and error correction module. The mechanism-driven approaches are denoted in the red color, and the data-driven approaches are denoted in the blue color. Now I would like to introduce the function of each module. data preprocessing module aims to find the key features through mechanism analysis and remove questionable data. We firstly carry out 50 times of MEF calculation on a well-known study case, the Barry Island electricity heat system in UK, which is shown on the right-hand side. And the corresponding model is adopted by many related publications. However, in the 50 samples of calculation, it is found that in parts of this case, the limit variation exists in the noodle temperature, which is illustrated in the figure on the left-hand side. This variation can significantly affect noodle temperature, resulting in non-convergence. Since we would like to train our model based on the simulation data, since we want to train our model based on the simulation data, we have to deal with the questionable data at first. Therefore, the mechanism analysis is carried out to find the critical cause and will be introduced in the next lab. Let me save the derivation of equations and directly give the answer of this issue by a figure. The figure at the bottom shows two simple lucid heating networks. The only difference between these two networks is the mass flow direction at pipe 2. These two networks represent two mass flow conditions. They are equivalent, and each one may appear during the calculation. However, the nonlinear physical model only supports one condition if both happen, which means the actual direction is different from the predefined direction in the model. The noodle balance equation will be violated, leading to the errors in the generated sample. To fix this problem, model reformulation is difficult since it involves more complicated mathematical problems. Therefore, we focus on customize the algorithm. Two decision procedures are added to the iterative process of the Newton method as illustrated in the figure. One is to check whether the mass flow rate is negative, and the other is to check whether the interacting node is a balanced node. If both are true, the noodle balance equation will be reformulated. Then we can avoid the errors in calculation. In order to provide basic linear models for the electricity heat system, nonlinear electrical and thermal equations are linearized based on a reasonable mechanism-driven simplification and an embedded data-driven linearization. The mechanism-driven model uses linearized electrical and thermal models as fundamental components of this dual-driven model. In the electrical network, the classical DC power flow equations are used with the assumptions of low active power losses, low resistance over reactance ratio for transmission lines, negligible voltage angle differences, and voltage magnitude close to 1 per unit. In the heating network, the heat loss is not considered since it is relatively minor in the network, approximately less than 4% in this case. The heat transfer equation and noodle heat balance equation are linearized based on this assumption. For the hydraulic equations, due to significant nonlinear characteristics, it is challenging to linearize them via mechanism-driven simplification. Ignoring the hydraulic equations may violate the loop pressure imbalance, leading to inaccurate mass flow rates, especially for meshed heating networks. Therefore, partial least square regression is used to extract the underlying linear relationship in hydraulic equations. The PLS regression is an effective regression approach that combines the advantages of principal component analysis with multivariate regression. It can better handle the data collinearity, which may lead to overfitting. These two modules provide a fast physics-guided calculation, but with unavoidable inaccuracy. At last, in the error correction module, a linear model is obtained from the regression of linearization error and further integrated with the previous linear models to improve the overall accuracy. Now we are in the case study section. In this slide, 3 linear models are compared, namely the mechanism-driven model, which only adopts linearization based on mechanism, the data-driven model, which is linearized only by neural regression, and our proposed dual-driven model. The result of original nonlinear model serves as a benchmark value. From the comparison, we can find that the dual-driven approach obtains the least mean absolute errors and mean absolute percentage errors of variables among all approaches in MEF calculation. Meanwhile, the calculation of electrical variables is significantly more accurate than that of the thermal and hydraulic variables, which implies a higher degree of linear relationship between the input and output variables. In this page, we are going to compare the error distribution of different models. The figure on the left side shows error distribution of variables calculated by data-driven approach and dual-driven approach, which are represented by red bars and blue bars. The 4 sub-figures show voltage angle, voltage magnitude, mass flow rate, and noodle temperature, respectively. As we can see in the figure, the error distribution of the dual-driven approach is significantly narrower and more to the left than that of the data-driven approach, which proves that the dual-driven approach has improved the accuracy. In addition, the accuracy of thermal and hydraulic variables is improved more significantly than that of electrical variables. These slides show stability of regression by data-driven and dual-driven methods. The figure illustrates relationship between model accuracy and sample size. We can observe that length of error at both sides declines significantly until the sample size of 50 is reached, which is nearly 1.2 times of the sum of electrical buses and heating mood. However, for the data-driven approach, which is on the right-hand side, the curves have significant fluctuations even after 50 samples, which shows that the dual-driven approach has more stable regression performance than the data-driven approach and different data volumes. At last, we are going to compare the goodness of fitting for data-driven and dual-driven methods through calculating the R-squared index for different variables. In regression, the R-squared index represents the coefficient of determination. It is a statistical measure of how well the regression prediction approximates the real data. It ranges from -1 to 1, and an R-squared of 1 indicates that the prediction perfectly fits the data. You can observe that higher nonlinearity exists in thermal and hydraulic calculation than in electrical calculation, which lowers the R-squared indices for electrical and hydraulic variables. Therefore, there is still room to improve the regression performance for thermal and hydraulic parts. Besides, also the IEF is considered to have more nonlinear characteristics than the power system. The dual-driven method effectively generates well-fitted linear models with the average arc index at about 0.85. To sum up, there are three advantages of the proposed dual-driven modeling approach. These advantages are the fast calculation speed, since it needs no iterations and initial values. Another advantage is as a linear model, it has good overall accuracy. It also supports fast training, since it has low requirements in sample size and training time. And it can be potentially applied in the following scenarios, such as a large number of repetitive calculations like probabilistic MEF analysis, N-1 contingency analysis, real-time security assessments, and so on. Other potential applications might be the optimal MEF calculation and the parameter-free modeling. In this page, I'd like to discuss some limitations of the proposed work. There may also be potential scientific problems in this area that deserve further exploration. First of all, the linearity. The accuracy of linear regression is reduced in systems with more severe nonlinear features, such as heating and gas networks. More advanced nonlinear fitting techniques can be used. However, they are usually much more expensive. The next one is dynamic. The dynamics of the heating network or gas network are significantly slower than the electricity network. The differential equations are more reasonable to describe the energy balance in heating and gaseous energy flow. The following three questions are doubts about the application of machine learning or data-driven methods in power flow or MEF calculation. The first one is interpretability. Data-driven mapping needs proper physical guidance and theoretical evaluation. Otherwise, they can hardly convince the operators and be employed in real application. The next one is reliability. Even if the overall accuracy meets the standard, unexpected errors may still happen and endanger the safety of the system. And the last one is adaptability. So we need to answer how to make data-driven models better adapt general variations, such as days and nights, and weather and seasons. Also, there exists some unfamiliar circumstances like network topology changes. Okay, now let's move to the third part. In this part, I will give a brief introduction of our recent work on a dual-level surrogate structure for solving the interval probabilistic MEF problem. The integration of electricity, heat, and gas involves abundant uncertainties, such as gas, water condition, the pipeline or transmission line properties, coefficients of equipment, surroundings, and so on, all with varying degrees of precision in their mathematical description due to different data richness in the real engineering circumstances. Therefore, the interval probabilistic description gives more flexibility to describe the uncertainty Therefore, it is of particular interest in an IES context because it provides appropriate models that include various sources of uncertainty without presenting unwarranted conclusions. When dealing with IPF, since existing analytical methods are easily caught in a quandary among accuracy, efficiency, and scope of applicability. Therefore, we propose a dual-level surrogate structure to deal with this problem. At the lower level of the dual-level surrogate structure, namely the DLSS, a sparse polynomial chaos expansion model is employed to directly map random input variables to output boundary values, saving massive repetition of deterministic calculation. At the upper level of DLSS, a heterogeneous Renyi-based multiple energy flow model is proposed to accelerate the indispensable deterministic MEF calculation for online sampling, therefore easing the computational burden of online sampling. Finally, results on a real-world electricity heat gas system demonstrate that the proposed DLSS can solve the IPF problem at nearly 400 times of speed of the benchmark method with guaranteed accuracy. This part is kind of, the part 3 is kind of oversimplified. Actually, I'll make more slides for this part. If you have further questions concerning this part, I hope this slide can help. Okay, that is the end of my presentation. Thank you very much for your attention.
Excellent. Thank you very much on behalf of mine, and I hope that the entire audience, I mean more than 50 attendees, could enjoy in your very interesting presentation on multi-energy flow solution by utilizing data-driven approach, in which you also make a comparison between these two approaches. So I would like to invite the audience now to ask questions to our presenter, Mr. Tian Hang. And please feel free to ask question. You can raise your hand. I see that.
Hi.
Yes.
Hi, can you hear me?
Okay, we see that Li Bing is talking. Am I right?
Yeah.
Okay, please ask your question.
Okay. Hi, Dr. Tian. Thank you for your presentation. And I have a question about what's a computational burden of the proposed approach, both for training and testing?
Okay. So if I understood you correctly, you would like to know the computational burden of this method. Am I right?
Yes.
Yes.
Okay. In our proposed model, we use the partial least squares, which is a linear regression technique, and it is computationally much cheaper than other techniques such as neural networks. And I think the training and testing time for about 500 samples will be quite short, possibly within 0.1 seconds on a personal computer. Okay, is that clear?
Yeah. Okay, thank you.
Thank you very much.
Professor, you are muted.
sorry, Mengshu Wang, you can unmute yourself and ask your question, please. If you are happy, we would be also happy to see you if you enable your camera, but it's up to you.
Hello, everyone. Hello, Dr. Tian. Thank you for your wonderful sharing in machinism of data-driven and dual-driven modeling approach, which gives me a new understanding of the research in this field. Here is a question I'd like to discuss with you. For an electricity heat integrated energy system, what is the difference between the calculation of dynamic energy flow and the steady energy flow when we use the dual-driven modeling approach?
Oh, okay. Okay. So this is a question about the difference between the
dynamic energy flow and the steady energy flow.
Okay, in the steady state energy flow and dynamic energy flow. So you mean, can we apply our method on these two type of models, right?
Yes.
Oh, okay. I think it's a very good question. My opinion is that it cannot be directly applied to the dynamic energy flow problem because the steady state MEF is to solve algebraic equations, and the dynamic MEF is to solve the differential equations. So they are actually two different mathematical problems. And the data-driven method we use here is linear regression. And someone may use neural networks to see the nonlinear features. However, they are kind of numerical mapping techniques, and I guess they cannot be directly applied on the differential equations. So currently, I have no clue about how the data-driven mapping can accommodate to the dynamic models. But it is indeed a very interesting question and maybe a new research direction. So if you have further interest in this problem, I'll try to find out this for you. Okay.
Thank you.
Thank you.
Excellent. Mengshu, if I can ask you, what is your research topic on which you are focused? What are you doing, please?
Recently I am working in the carbon emission tracing in the integrated energy system.
And who is your supervisor?
My supervisor is Professor Ma Zhou.
Aha, all right, good, excellent. Thanks for your question. And I wish you lots of success in your work. Maybe in the next seminar series from next spring, we could also have you as a presenter.
Oh, thank you.
Good. Okay, Wei Yu, please make a note. And so great. Thank you very much. So yes, good. The next question from Jihao Wang. Can you please unmute yourself? Eventually, if you'd like to show yourself on camera.
Yeah, Professor. Thank you for your excellent presentation.
Thank you.
My question is, since we have a lot of data from the system, can we use this data to speed up the iterative calculations such as Newton-Raphson or the state estimation? And can the data to be used to improve the performance of such schemes, or in addition to the data-driven methods?
Oh, okay. So you mean can we use the data to accelerate the state estimation?
The state estimation or the some other iterative scheme.
Iterative algorithm. About the iterative algorithm, like Newton method, currently I haven't read any reports on how to accelerate this method with the help from the data. But from my I have heard a lot of works on the data-driven method to speed up the state estimation. I think it's very popular. People may use some AI techniques, neural networks. I think there are many related literatures in this field about the state estimation. Yes. Do I make sense?
Okay, thank you.
Okay, thank you.
Okay.
Thank you, Jihao. By the way, Jihao, what is your research topic?
Professor, my research topic is about the fault rise-through of wind turbine energy coherent systems.
Yes, we had recently, I think, a paper.
Yeah, I have submitted a paper.
Oh, so we are still waiting for the response, are we?
Yeah, we are waiting for the, maybe it will be about a month to get the reply.
Yes, is it the second review, I think?
The third is the third review.
Third, it is IEEE transactions on sustainable energy.
Yeah, sustainable.
Okay. Thank you very much.
energy.
You see, my memory is not very good, but if you help me, then thank you very much for sending me the latest version. Thank you, Jihao. I know your surname, your name. Excellent. Weiyu, you'd like to ask a question, please unmute yourself. And
yes, Professor. I actually, my question is on behalf of Professor Jin Zhaoyang, because he has some problem with his microphone. So,
yes.
his question is about the accuracy of different approaches, because he said it seems that the mechanism-driven method is much more inaccurate than the data-driven method. So why is the dual-driven method, which is a combination of mechanism-driven and the data-driven method, better than the data-driven method? I'm not sure if I made myself clear.
Yes. I understand this question. It is indeed a very good question. It's to the point. In our work, we just make a simple combination of this mechanism model and a data-driven model. And data-driven model is used to fix the error and at the same time to keep the linear property of the model. And however, actually, we do not answer we do not make a good answer to that problem. Is how to combine the mechanism and the data-driven method correctly and perfectly. So it is we're still working on that issue. So I'd like to share more points after this talk. Okay. Thank you.
Okay. Thank you very much.
So thank you very much. I know that Professor Zhaoyang Jin is working and is expressing more interest on artificial intelligence and machine learning based techniques, and this is very good. So excellent. Zhaoyang will talk about that. Great. And I look forward to having more results in this research area. I'm very happy to now invite Stepan Vasilev, my PhD degree student from Skoltech, who is also expressing his interest in artificial intelligence and machine learning. Stepan, if you'd like to show you in the camera also, but unmute yourself and to ask your question, please.
Hello, everyone. Thank you, Mr. Hang, for your interesting report. And I have a question about metrics. There are many other metrics that can be used in your work, like mean average error or mean squared error. And my question is, I'm just curious, how did you justify the choice of the MAP metric in your work?
Sorry, you mean in the technique, the machine learning, the choice about the
yes,
choice about the machine learning technique. Okay, yeah. So we use this linear regression technique because it has a good performance in power system, and it is proved by some works, and we extend this thing to the multiple energy flow problem. However, despite the good performance of linear regression in the power system, it has its performance is lowered in other kind of energy flows like heating and gas, especially the gas networks. Therefore, we also use some nonlinear fitting techniques like neural networks, like deep networks and stacked diagnosing autoencoders to train to fit some nonlinear features, and it works good for the cases, but it's much more expensive for the training and testing, and it needs a much bigger data sample. So the linear regression, it is fast. It needs it has low requirements for data, but actually its accuracy is not better. It's not better than the neural networks from my perspective. Is that clear?
Yes, that's clear, but my question was about your 21st slide. Can you go back to it?
Sorry, what slide?
21st slide, please.
21, slide 21, number 21.
Okay. The slide.
Yes, can you share your screen and go? Yes, to go to slide number 21. Yes, great, thank you.
21. This one, right?
Yes.
Okay.
I asked about MAP metrics. I mean the seventh. Okay. Of MAP of lower upper boundaries. I asked about this, and why you have chose these metrics instead of other metrics.
I understand. So this part 3 is a new work. It's another work. In this work, we are trying to solve an interval probabilistic MEF calculation. So that problem is so in this problem, we can define it is different from the probabilistic energy flow problem. You can see in the table that based on the different degree of precise, imprecise, and deterministic and probabilistic, they can be divided into 4 problems. When the uncertainty is precise and deterministic, it is a deterministic energy flow problem. And when the uncertainty is probabilistic, it is actually a probabilistic energy flow problem. And there are also interval energy flow problems. So in this work, we consider the situation of both imprecise and probabilistic uncertainties. So this problem becomes a interval probabilistic energy flow problem. So the uncertain input will be a probability box. So it's in that shape. That box is composed of two CDF, cumulative distribution functions, two CDF. So the input is an CDF, the output is also an CDF. So in that box, any distribution is possible. So back to our back to this table, we choose the MAPE of the boundaries. It means the boundaries of this probability box is the accuracy of the box boundaries. Okay, do that make sense?
Stepan,
Yeah.
was it?
Can you hear me?
Yes, now we can. Now, yes, you will.
Yes.
Yeah.
Yes, it was clear. Thank you very much.
Thank you.
Okay, brilliant. Thank you for this discussion. Let me use this opportunity to ask my own question, which will go beyond these fine details. And I'd like, Hang, to ask you, what is the reason for integration of different energy systems? What is the reasons?
The reason of integration of multiple energy systems. One reason is that okay, I'll show my slide. One reason is that, as we can see, the renewable energy takes a large percentage of the power in the consumption of the power industry. However, the renewable energy in the heating and cooling is relatively lower. So if we combine all the systems together, we can increase the share of renewables in other systems, like the heating and cooling system. Another reason is that the heating and cooling system and also natural gas system, they have a relatively slow dynamics, and we can store the gas or hot water in their pipelines. It's kind of a storage. So if it is connected with the power system, we may utilize this storage applicability to accommodate such high penetration of renewables in the power system. That's my understanding, Professor.
Yes, I would like just to confirm. Yes, you're absolutely right. I fully agree. And your last statements are related to something what is described as flexibility of operation, so that through flexible operation we can increase utilization of renewable energy sources by utilizing, as mentioned, these storage capabilities, so that the profit of the entire process would be higher. Yes. So thank you very much for your response.
Thank you.
Any new questions from the audience? I'm very happy that we had quite a vibrant discussion. But yes, if not, actually we are about to finalize our meeting, where you know that we traditionally like to make a joint photograph in which we encourage all attendees to switch on their cameras. I will now invite everybody to do that, but Wei Yu, please repeat this kind question request in Chinese, please, so that we can make a joint photograph.
OK， 请大家打开一下摄像头。
Tomislav, lepo da te vidimo.
OK, if you have camera, please turn it on. Thank you.
It's nice to see also a young gentleman from Warwick. You're muted, Mr. Young gentleman.
Yeah, thank you very much, Vladimir. And greetings from my side.
You used to be with Shandong University. I am sure that some of students can recognize you.
Yes, I recognize Tian Hang as well.
Yeah.
Yeah.
Hi.
But
that's very good to
that's
very good to see the progress of your research is excellent. Well done.
Thank you. Thank you. We used to be in the same laboratory.
Yes, I had the privilege to be sitting in the same lab there.
316, the lab. Yeah.
Yes, it's quite yeah, that's right. That's very nice lab.
Very nice to see you.
Yes,
thank
you. It's very nice to see Tomislav from Belgrade. Tomislav, I'm in Belgrade as well. How are you, Tomislav? You're muted. You are muted, but I can recognize that you said something very nice.
Sorry. Hello, everyone. Thank you, Professor Terzia. It's nice weather here, and I fully enjoyed in this beautiful presentation.
Yes.
Thank you and our host, Shandong University and Skoltech University, to gathering us about this beautiful topic and to show that our science doesn't recognize any boundaries or limits between nations and countries. Thank you very much.
Absolutely. I also see my MSc student from Kazakhstan. Bakhtiar, how are you doing? How is in Kazakhstan? If you unmute yourself. You are muted. All right. I assume that you said hello to everybody. All right. Спасибо. Well, Jihua Guo, you are in Jinan, or maybe I didn't pronounce.
Yeah, Professor, I'm in Denmark now, and I will go back to China in about 10 days.
Oh, okay. Jihao, but
But Professor is asking Guo Jiahui, I think.
Sorry, okay. my pronunciation was not optimal. Sorry.
Yeah, I'm here.
In Jinan.
Yeah. Jiahui in Jinan. Yes, I'm in Jinan.
Jiahui. Sorry, I pronounced wrongly. I'm missing China and a bit exercise of Chinese language. I also see Mengxue Wang, you are in Shandong, in Jinan?
Yes. Hello, Professor.
Okay. Yes. Ni hao. Very nice. Good. Now, Wei Yu, it's now you to organize joint
now
photograph.
I'm taking the photo because most of the students are in their lab and without camera. So I'm now taking the photo. Okay, 3,
all right.
2, 1. Okay, I've taken the photo and I will send it to you.
Wonderful. Thank you very much. So just to remind all attendees that as a result of this seminar, we will issue a monography. It means a small book in which all presentations will be assembled together with extra 2-page summary of the presentation, with also my own introduction to everything, also particularly with Wei Yu's, with the Dr. Bao's opinion about everything, so that this will be everything, all efforts will result in a booklet which will summarize everything. Well, in this context, thank you very much. And please don't forget next Friday, 21st, 5 p.m. Beijing time, 12 o'clock Moscow time, 11 o'clock Belgrade time, 10 o'clock UK time. So thank you very much, and I wish you a very nice Friday afternoon, and of course, the coming weekend.
Thank you.
Thank you.
very
Bye
much,
bye.
Professor.
Bye-bye.
Goodbye, do widzenia. Do
Goodbye.
свидания.
Bye.
Bye bye.